Welcome to today's presentation on frontal crash design space exploration. My name is Karthik. I'm an advanced application support engineer on the HEATS design space exploration team at Siemens. We'll start today's presentation by discussing the motivation behind a crash optimization. Next, we'll take a closer look at what the underlying technology behind this optimization is. We'll then explore how an automotive crash workflow can be automated and leveraged for performing design space exploration through a frontal crash design space exploration case study. Lastly, I'll summarize the key points and the results of the case study. So without further ado, let's start with the motivation. Crash tests are performed to evaluate the safety of the vehicles under different impact conditions and provide insights into the protection offered by the vehicle itself. Two testing institutions, NHTSA and IIHS, rate the safety of these vehicles using different safety criterions based on these tests. Structural design and safety systems determine how well a vehicle protects its occupants. But this kind of destructive testing can be very costly and time-consuming for manufacturers, and hence, crash simulations using FEA are done to gauge safety performance of the vehicle first. This way, tests can be performed quickly and inexpensively in a computer before a real prototype of the car has to be manufactured. In this presentation, we'll explore a crash application to find an optimized design for a vehicle during frontal crash conditions. This design space exploration study aims at minimizing the mass of the vehicle while maximizing the energy absorbed, while simultaneously adhering to safety requirements like intrusion, head injury criteria, and chest severity index during a frontal crash. Now let's delve into the underlying technology for optimizing the frontal crash model. HEATS is a powerful multidisciplinary design analysis and optimization software solution that plays a crucial role in accelerating product development and reducing overall cost. By automating workflows and conducting design space exploration and optimization, HEATS streamlines the entire design process. HEATS offers several features that allow users to build simulation workflows using various commercial CAD and CAE packages. This enables automation of batch simulations, streamlining the optimization process. Users can define input parameters with specified ranges and specify the desired outputs for monitoring and/or improving performance upon. HEATS automation simplifies the process by automatically updating input files with new values from the optimization search framework, executing the entire simulation workflow, and extracting the relevant response values. These responses serve as foundation for defining objectives and constraints for the optimization problem. Another standard feature of HEATS is its unique and user-friendly optimization search framework that intelligently explores the design space by running multiple simulations with different parameter values. While the results are evaluated, local optima are refined, while also searching globally for other interesting solutions. For easy interpretation and analysis of results, HEATS provides a wide array of post-processing tools. These tools offer intuitive visualization capabilities, empowering engineers and designers to view high-performing designs and gain valuable insights with ease. There are 4 key enabling technologies that makes HEATS a great tool to help drive product innovation. Process automation enables the execution of CAD CAE tools without any manual intervention. The distributed execution capabilities allow for leveraging remote HPC resources to aid in faster computation. The state-of-the-art search framework Sherpa enables efficient search with its unique hybrid adaptive techniques. And a dedicated post-processor called HEATS Post comes with several post-processing tools to help gain insights from the data generated to compare the high-performing designs discovered by HEATS. HEATS works seamlessly with all the major CAD CAE tools and your internal software programs as well. We currently have direct portals to over 60 CAD CAE tools consisting of Siemens as well as non-Siemens tools. Here, we will utilize the LS Dyna portal for automating the crash simulation and the general portal to automate LS Prepost for advanced crash post-processing. However, it's important to note the versatility in connectivity Heat possesses to various solutions. Challenges related to design space exploration are analogous to the ones encountered during mountain climbing. When you are standing at the foot of a mountain thinking what all hurdles you might have to encounter, a natural question that arises is what tools or strategies you will need to overcome these hurdles. With a goal to reach the summit, it can be unclear what tools are needed with the limited visibility from the start point. This is exactly what traditionally is the case in conducting an optimization. After all, navigating a design landscape is like climbing a mountain where your goal is to scale a peak or a valley. Only now, the visibility of the terrain is even more obscured. So, based upon the anticipated terrain, we are tasked with picking a tool to help us achieve the summit. In the case of climbing the mountain, the selection of the tool is based upon the terrain at the base of the mountain. In the case of optimization, that tool is an algorithm and its setting. In reality, no single tool is typically adequate to reach the summit or even make some meaningful progress. What we really need is a Sherpa who knows all the strategies, carries all your equipment, and tailors the approach to the terrain encountered. They have done it before and can automate the journey to the summit. It also happens to be the name of the search framework deployed in Heat to help us reach our innovation goals. Sherpa is not an optimization algorithm but rather a search framework that is based on different search strategies and algorithms. It's hybrid in nature, meaning that it contains both local and global search strategies that are working simultaneously to explore the design space. This in itself makes Sherpa a powerful toolbox for automating discovery. However, Heat is adaptive in nature as well. It is continuously learning about the design space and tuning its strategies on the fly to explore the design space efficiently and dynamically. There is no need for the user to perform variable screening or model simplification or any kind of algorithm selection or tuning. Users can directly set up their models and start exploring better designs faster. Sherpa allows design space exploration or specifically optimization to be deployed as part of every design problem directly by the designers or the analysts responsible for making product decisions. If you look at where simulation engineers are spending most of their time during a project, you'll typically find something like this. By far, most of their time is spent building a baseline model and running the first simulation, resulting in significant manual interaction, lack of automation, complexity in connecting tools and setting up the process, oversimplification of geometry or physics to make things work, one-off results interpretation to decide what to try next. So much time is spent such that once they get their first result, there is little time left to look at design alternatives to improve product performance before making a design decision. Perhaps they can look at a handful of manual designs at best. What's required is a solution that is built with design space exploration in mind so that it allows engineers to spend most of their time where they can extract the most value, not on building and running the first model, but instead on exploring the design space to get necessary insights to make better decisions much earlier in the design process. As we transform this design process, we also need alternative approaches to understanding the data generated. Now, instead of a handful of designs, we are generating hundreds or even thousands of design alternatives. Heat's dedicated post-processor allows for automating data mining techniques that aid not only in selecting the best design for the application, but also better understand the design domain in general. It is critical that we change the paradigm on how post-processing is conducted with the design space exploration, leveraging tools and smart learning to data mine while still presenting in an automated fashion the analysis plots we are accustomed to. With an initiative to transform data into insight, a wide variety of tools are available in Heat's post to discover, gain insight, be equipped to make informed decisions including multiple plot types, plot synchronization, statistical methods, ROM generation, machine learning methods, and automated reports. Let's learn how each of these tools help transform data into insight in the subsequent topics. With an understanding of the tools to be leveraged, now let's dive into our frontal crash use case to see how we can leverage heats to discover safer vehicle designs faster. This frontal crash design phase exploration study aims at minimizing the mass of the vehicle while maximizing the energy absorbed while simultaneously adhering to safety requirements including intrusion, head injury criteria, and chest severity index. The requirements for each are specified here. This frontal crash design phase exploration study considers as variants only the crash critical components affecting the occupant safety to meet the frontal crash goals. This is done to avoid incorrect results which can be obtained if other load cases are not considered. For example, modal analysis, roof crash, or side impact, etc. We will be running a multi-objective trade-off study against our competing objectives. Let us quickly familiarize ourselves with our vehicle model. The model consists of a hybrid 3/5 percentile occupant positioned on the driver's side. A seatbelt with retractor, slip ring, and a sensor is set up to act as passive restraint for the occupant. Finally, an airbag is set up on the steering wheel which will inflate upon impact, providing passive restraint for the occupant. A frontal crash is performed on the full model with the occupant position with all these passive safety systems in place. The model is simulated for 140 milliseconds at an initial velocity of 35 miles per hour with necessary contacts for the occupant with the vehicle and the passive restraint safety systems. A baseline simulation file has been created using the relevant simulation tools. The explicit crash solution LS-DYNA is used here. HEATS, via its portals, interfaces with the given tools and will update the entire CAE pipeline based on the modified FE model, run the solution, and extract the results in an automated way. The mass and energy absorbed, which are our objectives, is assessed along with our safety constraints on intrusion, head injury criteria, and chest severity index. The baseline model, once validated, will be used as a starting point in building a workflow inside of HEATS. For further post-processing and ease of understanding our results, we run a downstream post-processing analysis to capture images and animation along with capturing our results for our safety constraints. This study has 11 thickness variables in total, which control the gauge of the crash critical components dictating the safety of the occupant. To achieve our goal of reducing vehicle mass and increase energy absorption, the following continuous variable ranges were set for the shell thickness variables. Additionally, we have another 11 variables controlling the material assignment of these crash critical components. Primarily, we use either steel or aluminum as our material choice. The material selection is done via discrete variables in HEATS for each crash critical component as shown here. Updated variable values from Sherpa go in as inputs into the FE model via the LS-DYNA portal. Once the frontal crash analysis is completed with the updated FE model, key responses including the vehicle mass, energy absorbed, are extracted automatically by the portal from the bin-out file. Further, the downstream post-processing analysis produces visualization files, animations, and extract results for the safety constraints in an automated fashion. As discussed earlier, HEATS can communicate with different machines on the same network, allowing for the utilization of remote compute resources. For this particular study, the FE jobs were remotely executed on a Linux HPC, while the post-processing steps were executed on the same local machine where HEATS study was running in an automated fashion. Out of the 600 designs evaluated in this study, 58 designs, or approximately 10% of the total evaluated designs, resulted in errors due to failed crash analysis. However, it is important to note that this does not impact the heat search process, as heat is specifically designed to focus on high-performing designed regions while efficiently navigating discontinuous design landscapes. As a result, a total of 348 feasible designs were found, representing 58% of the evaluated designs. Feasible designs here mean that all the requirements were met, while an infeasible design means that one or more of our requirements were not met for the given design. Here we have plotted both the feasible and infeasible designs in the design space, where along the x-axis we have one of our goals, mass, and along the y-axis we have our other goal, energy absorption. We can see there is a trade-off between these two competing goals. As we reduce the mass of our feasible solutions, our energy also decreases, which is undesired. Vice versa, as we increase the energy absorption of our feasible solutions, the mass increases, which is also undesired. It is this physical phenomena that was the underlying cause for us to run this design space exploration as a multi-objective trade-off optimization. As this is a trade-off study, it results in a Pareto front. As you can see, all designs on the Pareto front are feasible. A Pareto front represents a family of optimal solutions when competing goals are present. There are 20 design options to choose from on this Pareto front, each as an optimal solution depending on the ratio of energy absorbed over mass as desired. Stated differently, each design point on this plot represents a different level of trade-off between the vehicle mass and the energy absorbed by the system. We can see the performance of our baseline design and its distance from the Pareto front, indicating it as a low performance design in terms of our objectives. Here, design 537 is a high-performing design on the Pareto front, which has a 36% reduction in mass and 17% more energy absorbed when compared to the baseline performance. Design 456 is another high-performing design on the Pareto front, which has a 26% reduction in mass and 18% more energy absorbed when compared to the baseline performance. Design 423 is the highest performing design in terms of energy absorption, which is 28% more than the baseline design. However, we see that it has a higher mass when compared to the baseline performance. We have three groups of design candidates based on their performance with respect to our baseline design. The first group of design candidates have lower mass but less energy absorption than the baseline design. Next, we have the high-performing design group with lower mass than the baseline design and improved performance in terms of the energy absorbed. Finally, we have the third group of design candidates which have the highest performance in terms of energy absorption but have a higher mass than the baseline design. Let's look into what is similar and unique amongst these three family of designs. The radial plot here indicates where each design explored lies within the design space and the spread of each variable and response along with our objectives and safety constraints. Here we have all the non-error designs plotted. At the center of the plot is the minimum value explored and the exterior the maximum. The goals and requirements are highlighted with the rest of the parameters circumferentially being the variables. We can add on the plot the designs making up the Pareto front. If we focus on the requirements, here called out with the constraint boundaries, we can confirm that all of the Pareto designs are feasible in that they don't pass through the constraint boundary bars. We can see for the objectives that the Pareto designs encompass the maximum energy absorbed designs found, but that lower mass solutions were identified since none of the Pareto designs are at the center of the radial plot. This means that lower mass infeasible solutions were found, not meeting the requirements. If we focus on the variables, we see bands of solutions for some of the variables but broad coverage for others, indicative of variation in designs across the Pareto front. Here, we are highlighting the first group of designs identified on the Pareto front. Recall These were the lowest mass solutions. Then the second group of high-performing designs is shown. Finally, the last group of designs on the Pareto front is shown here. We have all three groups plotted here at once for comparative purposes. Now let's start to see what is unique about the given designs. When plotted with just the gauge thickness variables, we observe a trend that all Pareto designs are pushed into the upper range limits for the variable rail plate 1. Let's see what this means by interpreting it through another plot. If we focus on the gauge thickness for rail plate 1 as a color dimension on this plot, we can plot our feasible designs in a two-dimensional plot between the vehicle mass and the energy absorbed. We are able to confirm our observations from a radial plot that most high-performing designs are in the upper range for the values rail plate 1, making this an insightful find. If we return to the radial plots, similarly, we observe a trend that all Pareto designs are pushed into the lower range limits for the variable upper rail. Again, we can confirm this finding on a 2D relation plot in that most high-performing designs are in the lower range for upper rail as seen in the radial plot. Again, a crucial finding about the design landscape and our crash problem. When plotted with just the material choice variables on the radial plot, we observe a trend that all Pareto designs prefer steel as a material choice for the variable mat rail middle reinforcement 2. In fact, most of the feasible designs require steel as material choice for mat rail middle reinforcement 2 as shown here. Next, let's look at a different plot type to further gain insight into the variable influence on the results. The Boruta influence plot is a bar chart that compares relative importance among design variables for a given response. Here, the Boruta influence plot indicates that the change in material has a high influence on the total mass of the subassembly. This can be attributed to the contrasting densities between steel and aluminum. The Boruta influence plot also indicates that the change in material for rail inner has the highest influence on the energy absorption. The thickness of bumper frame and toe pan also have great influence on the energy absorption as well. The Boruta influence plot also indicates that the thickness of rail inner has great influence on the intrusion and head injury criteria. Material changes to rail inner and rail outer also have significant effect on intrusion and head injury criteria. The observations on the Boruta influence plot are confirmed here in a 2D relationship plot, which also indicates that a high thickness of rail inner or material changes to rail inner leads to higher intrusion. All of this serves as vital information in not only selecting the best design candidate for the given application, but in considering future design programs, tolerancing considerations, etc. While we have only demonstrated a few of the post-processing techniques here, hopefully it is evident of the type of insight and discovery that data mining capabilities of heats post can unlock. As it pertains to the problem at hand, with just a single run, Heats has identified a family of optimized designs. Based upon the insights drawn, design trends, and key variable identification, the user can make informed trade-off decisions, allowing for the selection of a design with high energy absorption and lightweight while satisfying crash safety requirements. Let us now summarize key features and findings demonstrated in this case study. The virtual prototyping workflow encompassing a crash simulation has been successfully developed and automated through the utilization of direct portals through Heats. This automation ensures a seamless and efficient process, allowing for direct setup and configuration. The parallel execution capabilities and remote hardware utilization capabilities of Heats facilitated a significantly reduced turnaround time for this design space exploration study. This allowed for faster and more efficient computation, ultimately leading to accelerated results and improved productivity. Through the utilization of Heats, a Pareto front of design showcasing enhanced performance in terms of both objectives was successfully discovered. 3 design groups were identified with varying performances in objectives when compared to the baseline design. By employing post-processing tools in heat sports, we were able to identify important trends and crucial parameters that play a critical role in optimizing design performance. By combining heats with CAE tools, we were able to develop a multidisciplinary workflow where high-performing vehicle model designs were identified quickly and confidently. Further details on setting up and running this particular problem, a detailed heat quick start video is available upon request or via the customer portal. This concludes today's presentation. Please feel free to contact me if you have any questions about this application or the applicability of heats to your problems. Comprehensive documentation and a wide range of learning resources can be found on the Siemens Support Center as well as the dedicated Heats customer portal. These valuable resources provide detailed information and guidance to help users effectively navigate and leverage the capabilities of Heats. Whether you need technical documentation, tutorials, or additional support, these platforms serve as valuable knowledge hubs for all your Heats-related inquiries. Please note our new support alias in case you need to reach out to Global Heat Support Network for support using Heats. Thank you.